So what we are going to do in the first programming screencast is we are going to take a small world network in one dimension, which we have discussed already. What is that? That is first of all a ring. So I'm going to take a simple ring. By simple ring I mean one node on this ring. For example, this node here is connected to only one node towards its left and one node towards its right. So I'm going to take this simple ring, and then what we are going to do is we are going to perform two kind of search on this network. So first of all, by the side of these ties which are homophily based, there will be weak ties, something like this. So let me put two weak ties in this network. So these yellow lines are the weak ties here, and these are the homophily based ties. What we are going to do next is we are going to choose two nodes. So I choose here two nodes, let's say this, and I call this node as source, and then I choose, let's say, this node, and then I call this node as destination. So for going from source to destination here, we have two kind of searches which we have discussed before. So we are going to implement those two kinds of searches. The first one is the myopic search, and the second one is the optimal search. From our previous discussion, we know that myopic search is not always optimal. In this particular case, yes, the myopic search is optimal. So here myopic search will also give you the result. You go from here and then you move here, and optimal search is also going to give you the same result. However, there can be cases where their results differ, as we have seen an example previously. What we are going to do in this programming screencast is we are going to take a small world network, one dimensional ring on 100 nodes. So let's say my label start from 0. So 0, 1, 2, so on, and something like 49 here, and then 50, and then there comes 98, 99. So I'm going to take this ring first of all. So these are my homophily based ties, and we are going to put across 10 weak ties here. So I put 10 weak ties here, 10 long range contacts, 10 weak ties. Next, what is our aim? Our aim is to compare the myopic search with the optimal search for various different pairs. So which pairs do we choose? So we want many pairs for source and destination, and we are going to check for all these pairs what is the difference between the path taken by the myopic search and the path taken by the optimal search. We think that the best pairs for doing this are the pairs which are diametrically opposite. Why? Because along this ring they are at the highest distance from each other. So we can take 0 and 49, and then 1 and 50. So these kind of pairs we are going to take. So what we will be doing, we will be taking the pairs 0, 49, 1, 50, so on and so forth up to 50, 99. So these are going to be, I guess, 51 pairs. So we are going to take these 51 pairs, and then what we are going to do is we are going to draw a plot. What is this plot? On the x-axis here are my pairs. So this point here can correspond to my pair 0, 49. This point can be 1, 50, 2, 51, so on and so forth, 50, 99. So the x-axis denotes these pairs, and across the y-axis we are going to draw two results. So the first result is corresponding to the myopic search. So we'll take this pair 0 and 49, and on this ring we will calculate what will be the length of the path taken by myopic search. So might be myopic search goes from 0 to 1, 1 to 2, and 2 to 49. In this case, the length of the path will be 3, right? So we'll see what is the length of the path taken by myopic search and plot that somewhere here. And then for 1, 50, 2, 51, so on and so forth. So we are going to see what answer our myopic search gives us, and we are also going to draw a plot corresponding to the optimal search on the same plot. So for 0,49, what was the path of the length given by optimal search for 1,50, so on and so forth, and we will be observing how this plot looks like in reality. Okay, so what I am going to do now is I will be taking one array. So this array is for my path lengths corresponding to the myopic search. Path lengths corresponding to the myopic search, and I'll be having an array O, and this array O is for the path lengths corresponding to the optimal search, and then I'll be having an array X, and this X array is simply for the X-axis, and as we have seen previously, each point on X-axis is nothing but one pair of nodes, and this one pair of nodes is something like it will be 0 and 49, or it will be 1 and 50, so on and so forth. So it will be a pair of diametrically opposite nodes. So that is my X-axis. What I'll do next is I'll take a new array, a point t here. T is initially equal to 0. And next what I'm going to do is, the use of t you will come to know soon. What I'll do next is, I know my first node here, so we are going to change. So previously we have looked at the distance from 0 to 40. Now we have to look the distance between all the diametrically opposite nodes. So I'll say my first node is u. So for u in range, and this range is from 0 to 49. 0 to 49. And for this, what I'm going to do is my second, which is a target node. So u is the source node and target node is the diametrically opposite node, and we can find it out by adding 50 to this u. So how the pair will look like? Corresponding to 0, it will be 50. So a little bit change here. Corresponding to 0, it will be 50. Corresponding to 1, it will be 51. So on and so forth. And next what I will be doing is, first I will perform a myopic search here. Myopic search not from 0 to 40 but from u to v. And next I am going to do an optimal search here, which is again going to be from u to v. So I have got the path according to my myopic search and I get the path according to my optimal search. And we don't need all these lines here, so I'll delete them. Okay. Next what I will do, in my array M, which was corresponding to the myopic search, I will append the length of the path which I got from the myopic search, and in my array O, I will append the length of the path which I got from my optimal search, which is length of P1. And across the x-axis, I'll simply append t because we need some numbers across the x-axis, and I'll increment this t by 1. And next what I have to do is, I have to simply plot this. So I plot plt.plot. I plot myopic search, the path length corresponding to the myopic search on the x-axis. So x, m, and let's say it should appear in red color. So my myopic search appears in red color on this plot, and plt.plot, and then x, and optimal, the path length corresponding to the optimal search occurs in blue color, and then I simply visualize this plot. Let's run this code and see. Python ring.py. Yeah, so you can see here red colors are corresponding to the myopic search. So we have taken around 50 pairs of diametrically opposite nodes, and we can always see that most of the times the myopic search takes quite a
a large number of steps as compared to the optimal algorithm. However, there are many points where myopic search actually performs optimally. So out of these 50 points, there are 11 points on which our myopic search it also performs optimally. So this was the plot we wanted to look at.